Hello Year 12 chemists, welcome to TP's Chemistry Cuts. In this clip we introduce the concept of oxidation numbers and then go on to use a set of simple rules to calculate them.
The problem, as I say, for us is how do we know if we've got something that's a molecule whether electrons are being transferred from it or to it? It's very easy if we look at ionic species because they've got charges, and if the charge goes up and down you know it's either gained or lost an electron. So what we do is we change everything into a charged atom, okay? Even the atoms in a molecule. So the first step I did in that, right at the very beginning, when I separated the ions for an ionic compound, we now then go ahead and do for every single species, every single atom of every species in that reaction. We separate them. The problem is, what do you do if you've got two electrons shared in a bond? And this is where it becomes a little contrived. What you do is you allow for electronegativity. So the more electronegative element gets both electrons. It's as simple as that. So if you've got oxygen and hydrogen, you take the hydrogen away, the oxygen gets both of those two electrons. Okay? And what you end up with is a series of atoms with charges on them. And those charges are the oxidation numbers. So literally, they're the charge on an atom allowing for things like electronegativity or whether electrons have been gained or lost prior to that thing forming. Okay? So let's write that down. You don't need to have to explain this, you just need to be able to use them. It gives you some idea of what they are. Okay, so let's see how this works. If we add NaCl, then if we separate those ions, we get Na plus and Cl minus. If we've got H2O, okay, like that, what we get is two H pluses because they're the less electronegative element, and we get an O2 minus. Okay. Now we'll go through some rules to explain how we get oxidation numbers in a minute, but if we look at the oxidation number for this, it's +1, this one it's -1, each of these is +1 for each H+. And that's the important thing. If you've got a whole load, say you've got something with 5 hydrogen atoms in, we're only interested in the oxidation number that each one has, not the total sum of them, just each one. And for oxygen, this would be -2. So that's how the oxidation numbers work. And it's a very simple exercise. Once you've allocated oxidation numbers to each type of atom in a reaction, you compare the oxidation numbers before the reaction with the numbers afterwards for each type of atom. And any one where they've gone up, it's been oxidized, and every one where it's gone down, it's been reduced. And that's where the word reduce comes from, because you're reducing the size of the number. Let's develop a set of rules that will help us to very easily work out oxidation numbers. And we need a starting point. At what point do we have 0 as an oxidation number? And that should be straightforward. An oxidation number of 0 means that we have an atom in its elemental state. If we take an atom in its elemental state, like oxygen, separate those two oxygen atoms, each oxygen atom must get 1 electron. You can't give them to 1 because it's not more electronegative than the other. They're the same. Okay? Which means that there's an overall charge of 0. And so the oxidation number is 0. So in other words, that's the starting point. Okay? If you think about it, everything it was originally in its elemental form and it's reacted. And so if it loses electrons, it's going to go plus, so it will go up, which means it will oxidize. If it gains, it goes negative, which means it goes down. So it's reduced. So our sort of standard point, the point of 0, is when any element is it has an oxidation number of 0. And that's our first rule. Okay? So let's put this up then. Rules for determining oxidation number. Oxidation rules for working out oxidation numbers. There are only 5, so don't worry, it's not going to be a whole long list of these things. And before I go on, I should make it very clear, you may come across the phrase oxidation state. It means exactly the same thing. Oxidation state, oxidation number, no difference. Okay? So, 1. And this makes sense, really, because if you want to put it in very simple terms, anything in its elemental state is unreacted. So that's just saying that's 0. So, and it doesn't matter if it's a metal or a non-metal. It doesn't matter if it's a non-metal and it's molecular, how many atoms there are in that molecule. It's still just each atom has an oxidation number of 0. So if we take something like O2, each of those 2 oxygen atoms has an oxidation number of 0. There's an allotrope of oxygen called ozone, which you all know about. Doesn't work for us, does it? At the moment, there's a big gap above us, and we're getting soon be time for slip, slap, slop. But even for ozone, all 3 oxygen atoms, the oxidation number is 0. Okay? If we look at something like sodium, metal, oxidation number is 0, and so on. It can be something gold. Let's go exotic, shall we? Sulfur in its elemental form is S8. Each of those sulfurs is oxidation number of 0. So that's the first rule. So we'll start with simple. Okay. So if we look at monatomic ions, what do we mean by monatomic ions? One atom that has an overall charge. Okay, so it makes sense then if elemental atoms are 0, the charge on an ion is actually the oxidation number if it's just a single atom. So if we take, for example, Cl minus, the oxidation number is -1. If we have Al3 plus, it's equal to +3. Notice that I always put the plus in front of them, even if it's not necessary. It just puts it in your mind. You're distinguishing between plus and minus. Get into the habit of it. It's probably a good habit to get into. And so on. So, what about molecules? That's where things start to get a little bit more challenging. And it turns out, for most of the things that we will deal with, you only need a couple of rules for it. And so, if you've got a molecule with H atoms in it, then the H atom is always +1. It goes without saying, of course, it excludes H2 in its elemental form, but we're looking at anything else other than hydrogen in its elemental form. And the reason I put those 2 examples up is to emphasize the fact we're talking about each individual atom in those molecules. Okay? And that's what you're always going to be talking about, is the oxidation number of an individual atom, because all of them in that given molecule will be the same, but you only need to know one of them. So that's our first one. And you'll find that that covers an enormous number of molecules, not quite enough though. So the second one that we have is oxygen. Okay, now oxygen is where we get an exception. If we deal with anything other than hydrogen peroxide, H2O2, and unfortunately H2O2 is something that we'll be dealing with all the time. It's an unusual molecule because it can act as an oxidant or a reductant, as you'll see. Then, if we ignore that one for the moment, anything else that's a molecular compound that contains oxygen is going to be -2. So the same as oxide, if you like. But in hydrogen peroxide, it's -1. And I really would emphasize that because that's the one that people often forget. Now, between them, these two rules will help us determine just about anything else, surprisingly. I think that that's not an awful lot to know, but they do. Because we're going to use two more rules which make use of these two. Okay. So if we're looking at neutral molecules, okay, if you take the sum of the oxidation numbers for every atom in that molecule, add them all together, it must come to 0. Okay? And this is where some algebra is needed. So let's look at a couple of very straightforward examples. Okay? If we look at H2O, that's 2 times H plus, or 2 times H plus 1 times O. Yeah? So that's equal to 2 times +1 plus -2, which is equal to 0. But that's just to show you that it really does work. Okay? And for H2O2, that's equal to 2 times H, which we've been told before is always going to be +1, plus 1 times O.
So is it 2 O's?
Yep. Okay, sorry, 2 times O, you're right. So, from rule 1, we've got 2 times +1. Sorry, not rule 1, rule 3. And then from rule 4, that's not rule 2, it's rule 4, I'm having a mad, yeah. From rule 4, we're now dealing with hydrogen peroxide. So we've got -1 for oxygen here. This is the exception. So we've got +2 times -1, and that again is 0. Okay? So I've got 2 times +1, 2 times -1, which is 0. So I've got +1 from here, -1 from here. Alright? Right. So let's use that one to work out a few more oxidation numbers. Try all of those. Okay? Try those. Done those, I can add a few more in. So, for the benefit of those who can't do maths at all, this is a simple bit of algebra. So you've got 1 times n plus 3 times plus 1, which is rule 2, is equal to 0, which is rule 4. Okay, so I'm using that rule and this rule, which means that n is equal to minus 3. Does that make sense? Now can you do the rest? 2 times n plus 4 times plus 1 equals 0.
Do you have to work the whole thing out?
I'm just showing you how it works out. Okay? Which means that 2n is minus 4. 2n equals 4 times plus 1. So you put it onto this. Do you want to go to see your maths teacher now? 2n plus 4 equals 0 for the benefit of you. Yeah? 2n equals minus 4, so n equals minus 2. That's just simple algebra. So this one is n, 1 times n, plus, and this is minus 2. 1 times minus 2 equals 0, so n equals plus 2. So you've gone from minus 3 to plus 2 with n. So this isn't a real thing, because it's still nitrogen. Okay. Then you've got 1 times n plus 2 times minus 2 is equal to 0. Does that make sense? Okay, so n minus 4 equals 0, so n equals plus 4. Yeah? You're frowning. It's n. 2 times minus 2 is minus 4. And then you've got minus 4 here, so you've got to move it over to here, so it's plus 4. Good. This one is 1 times plus 1 plus 1 times Cl equals 0, so Cl equals minus 1. Yeah? This is 1 times C plus 4 times plus 1 equals 0, so C equals minus 4. 0. And you got 2 times C plus 4 times plus 1 equals 0. So C equals minus 2. So I'm just going to do the rest. That's going to be minus 2. Yeah? Okay? Just quickly put those in.
Isn't the first one a negative?
So that's probably what confused me. So, now, what that actually means then, if we take one of those, which one should we take? Which one has confused anyone? The second one. The actual structure of that's hydrazine. Okay? That's actually called hydrazine. What it's telling you is that what we've got is this is plus 1, this is plus 1, this is plus 1, this is plus 1, And then we've worked out that each one is minus 2. Okay? Add all those numbers up together and what do you get? 0. That's what it means. So if we looked at, say, C2H4, which you should all know the structure of, which is ethene. Okay. Let's put in the values. Plus 1, plus 1, plus 1, plus 1. Okay. And we've got, for the carbons, we've got what? Minus 2. Minus 2. Add them all up together. 0. So that's what it means. What we've done is we've separated all those atoms and made them into ions. It's not a real thing, but it's what we can use to help us identify transfer of electrons from this species to another one. Now, what we have to do now is the final rule, okay? And it follows on from this one here, number 5, and it deals with things that have got an overall charge to them, but also contain covalent bonds. And you'll have come across things like that. Can anyone give me an example? Something that's got covalent bonds in it, but has an overall charge.
Graphite?
You're overthinking this. Yeah? NO3 minus, SO4 2 minus, OH minus, and there's going to be some more exotic things as well, as you'll see. Number 6. Let's have a look at something exotic, because this is going to be used to work out things that are a little bit more unusual, because often the things that we deal with in redox reactions are things you've not come across so far. So we're going to look at dichromate. Okay. Potassium dichromate is like that. Okay. So that's potassium dichromate. What do I need to do first and foremost for that? What did I say? Very first thing, highlighted. What type of compound is that? What type of compound? Look at the formula. Tell me what type of compound it is. It's ionic. Okay. So we need to separate the ions, because that's neutral at the moment, isn't it? So we must separate the ions. I can see why you're hesitant, because the anions are a little bit different to what you've had before. So you've got 2 K pluses there. Okay. And then you've got a Cr2O72 minus. And this is what causes all sorts of confusion. You'll find you'll get K pluses and Cl minuses and things. They're just spectator ions which are balancing charges, but they're not actually going to be oxidised or reduced themselves, so you've got to remove them. And so if you see something like this and you try to do a redox equation based on this, it will probably end up being wrong. So you need to separate out the ions and then get rid of the spectator ions, because they're not part of the reaction. Okay? So what we know, because this is all 2 times plus 1, that's straightforward. It's a monatomic ion, so we can forget it. What we're interested in is a molecular ion. Okay? Now, this is where things get a little bit grayer, because what we're looking at now are transition elements. They're the ones that are in the range from scandium to zinc. And they're called transition elements because they're a transition between the metals on the left and the non-metals on the right. And one of the things that makes them sort of intermediate is that they can covalently bond and have ions as well. And this is a mixture of the two. So they've got covalent bonds and ions, okay? And it's ionic. But things like iron can form these sorts of things, but it also forms monatomic ions as well. Okay, so it's a bit of everything. That is university level stuff, so you don't need to get too worried about it. What you'll come across is this ion time and time again, and that's actually wrong. It should be 2 chromiums there. And we're going to work out the oxidation number of the chromium, because we know what oxygen is. What is it? -2. So what we're saying with this rule is that 2 times Cr plus 7 times O is equal to -2, because that's the overall charge. So we've got 2 Cr plus 7 times -2 equals -2. I'm taking this really slowly so you get it right. So 2 Cr minus 14 equals -2. 2 Cr equals 12 plus 12. So Cr is equal to plus 6. So if we were to draw that out, you've got 2 times plus 6, which is plus 12, plus 7 times -2, so that's minus 14. So plus 12 minus 14 is -2, which is the overall charge, which is the way it works. Nicely. So why don't you try this one, because you're going to come across this one time and time again. Potassium permanganate. That's the purple stuff. So what's the first thing you do? Separate them, yes. What's the betting everybody forgets that? So it's plus 6.
Is it not -1?
So just checking, see if everybody's awake. 7. Oh my gosh, I need coffee. Okay, so you want to do some more practice?
What if it's a compound with 3 or more different elements and it has an overall charge?
Yeah, because there are 2 oxygen.
We do that.
Oh.
Okay.
So therefore, K has a +1 charge. Yeah, but if you look at the next one down below,
How about baking soda?
Sounds good.
then there's only a 1
Go for it.
I don't know.
If we deal with this one then, taking that on board, this is going to be sodium plus. And then you've got HCO3 minus. Okay? Which is what we're interested in the first place. So we can ignore that because it's just going to be +1. And it's a spectator ion. So this is going to be equal to -1. So we've got +1 plus C plus 3 times -2. So it's just algebra. Okay, 3 times -2 is -6, plus 1 is -5. So you've got C is +4.